Jason Wang, Ethan Wu, and Richard Wang.
Good afternoon. We are Miracle, and I'm Ren Jingyang. This is our captain, Tim Chen. This is Yu Zeyan, and this is Ren. Hope you enjoy.
Okay, let me briefly introduce our jury today. The jury is
I'm Zheng Wenze from Hengkang University.
Hello, everybody. My name is Lin Zifan from National Academy University.
Okay, so Chen Jianqun from Department of Engineering and System Science in Tsinghua University.
I'm Pei-Shun Jiang from National Taiwan Normal University.
Okay, and myself is the Xi Mingzhi from National Chongqing University in Physics Department. Okay, so thank you. So they're starting from the opponent to change the reporter. So. Problem number 17. Problem number 17. What problem is that? Classical chain reaction. Reject. So the opponent change again. Problem number 2, aerosols. Reject. Repose or reject again. Problem number 6, hurricane body. Second? Okay, so we have 5 minutes for preparation. Okay, so please write your name or
Problem number.六。
You can start whenever you are ready.
Hello, my name is Ryan, and I'll be presenting per keyboard. So the problem statement is that two steel balls that are joined together can be spun at incredibly high frequencies. By first spinning them by hand and then going them through a for example, a computing chart. Explain and investigate this. So the introduction is that a protein ball system is approximately that of a gyroscope. In that, first, you have a particular velocity that points in this direction, and then a torque that points in, a gravitational torque that points in that direction. And then this allows the gyroscope to stay at a constant angle and then to rotate around the z-axis. This is approximately describing the motion of the particle. So, the first thing I need to introduce to you is the coordinate system that we're going to be using for my hearing. We're going to use a rotating frame, which is defined by three axes: EZ pointing that direction, E3 pointing that direction, and E2 pointing outside the cage. The y-axis is also pointing outside the cage. Okay, so one assumption that we're going to make is that there will be no slipping. And making that assumption, we know that R of 5 and R of psi will be both equal to cosine of theta. Therefore, basically the angular velocity of these two should phi and psi should be the same. Okay, go on. So in the E1 axis, you should see a spin like this. And then in the E3 axis, you should see a spinning like that. You should see a spinning like that. So just like the gyroscope, there's also a gravitational torque that's applied that goes into the board. And this gravitational torque is equal to 2 mv sine of theta. And it points into the board in the E2 direction. The angular velocity is shown here. We can clearly see that the gravitational torque is perpendicular to the angular velocity. That means that the gravitational torque will not result in any change in angular velocity. Instead, it will cause the hurricane ball to essentially precess. That means that the angle here will stay constant if no other external torque is applied. So now we're going to talk about some assumptions that we make. The first assumption is that the center of mass will not change unless the velocity of the ball is moved by an external force. So basically, if you push the hurricane ball, then obviously the center of mass will change. But basically, the center of mass won't change unless you push it or something with a force. And then the magnus effect in turbulence in the coming slides will be thought as negligible. And the third assumption is that there will be no slipping. The fourth assumption is that the ball is displaced by an external force. The external force will not contribute any torque. So let's say if I blow the hurricane ball, then the hurricane ball moves. The movement of the ball will not contribute any torque. So how are we going to analyze the effects of the torque on the angular velocity? How we do it is first we find the angular velocity using the definitions. And we break down the angular velocities into their components in the spinning frames. And then we multiply that by the diagonalized moment of inertia tensor. And then when we do that, we get the angular momentum. What we want to do is we want to take the derivative of the angular momentum in order to get the torque. You learn, and I'm sure that you've all learned that the derivative of the angular momentum is equal. What's hard about this is that the derivative of E1 and E3 is non-trivial because they are in fact moving. So what we did is we essentially made a rotational matrix that related E1 to EX, EY, and EZ. And then we took the derivative like that. Since the EX, EY, and EZ frame won't change over time, the derivative of that will be totally valid. And from that relationship, we know that E1 is equal to cosine of theta times that's psi times E2. And then E3, the derivative of E3 frame is equal to negative sine of theta times psi dot of E2. Using that information, we can relate the torque to the angular velocity and angular acceleration. And since the gravitational torque is equal to that torque, we can relate this term here, which is basically the angular momentum, the torque term, to the gravitational torque. And when we relate this term here to the gravitational torque, then we can get a relationship that cosine of theta is defined by 2 over 5 minus g divided by angular velocity squared times r. This is a result that has been confirmed by many research papers, so it is a accepted result. In this case, we also assume that the angular velocity, there's no external torque apart from gravity that is being applied on this board. If we assume that if we assume that the change in, that there's a angular acceleration in the E1 and E3 frame. And then we have, actually first, sorry. We need to introduce a concept called the tangential force. When we have two balls and then we apply a force on the top ball in the E2 direction, there will be a torque called the tangential force, which will eventually change the angular acceleration and angular velocity of the system. So since we assume that the angular velocity of phi and psi are both the same, the angular acceleration of those two should also be the same. But there actually isn't any torque that causes E3 to swing faster, except for static friction. So what we did was we used we related these two equations together, these two terms together using static friction, and then we got the final solution for go back there, which is this entire term. And this will tell us, this is a differential equation that will tell us basically the angular acceleration over time. Oh no, sorry, the angular velocity over time. So the forces that can be applied, the tangential forces that can be applied to the ball are rolling resistance. That we need to consider is that rolling resistor, the air compressor jet, which is the force of the air compressor, and then air friction. And how? Okay, now we're going to go into the experimental part. How we build the hurricane balls is by gluing two steel balls together using hot glue. We only use one set of balls with a radius of 1 centimeter and a mass of 130 kilograms. So in the first part of the experiment, we use a laser tachometer to control our initial velocity. We spun it up to a preset initial velocity. Then we use the iPhone to record a slow motion footage of the hurricane ball and to see the process of the hurricane ball slowing down. In that case, there are two forces applied to the hurricane ball. One is the rolling resistance, and the other one is the air friction. This is our video analysis software. We now use Tracker. This is me doing the experiment. You need that? Okay. So experimental data. Our initial angular velocity is 104 radians per second, and this is our map. And this is our data over time. So we can see that the angular velocity decreases over time in a very linear manner. However, this is not actually a linear term. It is only linear because rolling resistance is very big compared to the air friction. So that means that since the rolling resistance is almost a constant force, the angular velocity decrease almost linear. Angle versus time looks very problematic. This does not match, this does not match. The whole doesn't match. But we can relate this to this can be explained, however, by the next time. We've already talked about the theory of let's consider now something we haven't considered before, which is the ground effect and the Magnus effect. The ground effect basically says that when your hurricane ball goes closer to the ground, there will be more lift force. And then the Magnus force is just a force that goes up. And then it will present a force that's opposing to gravity. So it kind of lifts the ball back. By considering the Magnus force, we end up with a very well-fitted we did two other experiments on how long it takes for the hurricane ball to fall with a set angular velocity, and then how the angular velocity after 10 seconds. And these are actually relatively. So now the second part is measuring the relationship between the angular velocity and the air velocity. We measure the air velocity by basically just seeing how much force is applied to the ball, and then we can use that relationship to find the velocity. Now, this is basically our force equation, and this force equation predicts a trend that looks like this, which makes sense because as the angular velocity goes higher, the force on the ball should be smaller. Okay. And then this is our experiment, this is our theory, and then our theory isn't exactly linear. However, we notice that we can approximate this trend using a linear trend. So our end result was we used a linear approximation for our experimental data, and it was a very good fit. So future direction include like experimentally determine some of the unknown concepts that we haven't talked about, and observing the effects of different size hurricane balls, observing the effects of different surfaces on the hurricane ball.
Time's up. So time for opponent to have question.
First of all, you said you didn't consider any external force in your theory.
No, external forces that causes a displacement. Only external forces that cause a displacement. We do not consider that. If you consider a force that's in the E2 direction, like the two balls here, we apply a force here, the ball will spin faster, but it won't move. We're not considering forces that will move.
So you said that the two angular velocity on two directions will be the same.
Yes.
Right?
Yes.
Do you have any experiment that shows that they are the same?
And I'll go back. During our video analysis, we noticed that the ball spins. One revolution and this.
Do you have the data for this? Can you show me that they are actually the same?
The actual data.
Yes.
We did not include that in the.
But they do this experiment to make sure that they are the same.
Yes. This is also confirmed by other research papers. We did not base it on all the The specific research paper is Dickinson.
Yeah. You said that in your experiment you change the rolling resistance and you consider the drag of the wind and you consider the drag and the force from the wind, right?
Force on what?
Wind blowing up the balls.
Yes.
But how can that cause an external force? Since we didn't consider that.
We're saying that if basically what we're arguing is that
Okay, time's up. So 3 minutes for the opponent to prepare.
I'm the opponent from Team Miracle, and today I'm going to propose problem number 6, critical balls. This is a problem statement. It tells us to use two steel balls that are joined together, and we can count it by first spinning them by our hand and then by blowing on them. So I think the crucial part about this problem is that, first of all, you need two steel balls that are joined together, and then they can be spun at a high frequency. And also the problem statement tells us about starting by spinning them by hand and then blowing on them. And then blowing on them with a tube. So I think these are some crucial points for this problem. This is my opinion on the strategy for solving this problem. First of all, they should explain clearly about this phenomenon, how it happens and how the ball moves the way it does. And then I think that the reporter should tell us about his setup, about the steel balls and how he's going to swing onto the balls and how he controls it. And finally, he should do various parameters and also calculate the theory and check if they fit. Okay, here's the reporter's pros and cons. The pros are that, first of all, the reporter has a clear presentation. And secondly, he shows some correlation from his theory. The cons are that, first of all, the theory didn't consider, as he said, the external torques. So I think that is too ideal assumption, and that couldn't be practical in the real life. Also, I think that the reporter's presentation contains too less experiments and too much theory. And even more, it didn't seem to have an adequate amount of theory line for fitting line to prove that his theory fits the experimental results. Okay, so here's a discussion point I will make in the following discussion. First of all, I'm going to discuss. Let's talk about. In your theory, you don't consider any external torque, right?
No.
Please
We
explain.
assume no, we did not consider external torque that causes a displacement of the hurling ball. A torque that moves the ball.
Okay, so you still consider some torque, right?
We considered three torques. One is on the air velocity, one is on the rolling resistance, the other one is air drag.
So you're sure that all of these three will move the center of the ball?
Actually, the air compressor will move the ball. But let's look at this way. When you move a ball, like translation, would that cause a torque?
Because you then talk about the rotation of the balls.
If you move something across, will it cause a torque?
No, but you didn't determine that. But in your experiment, it wouldn't be always so ideal, right?
Yeah, so we were saying that
still might cause the ball to speed or accelerate, and that is what the problem statement asks us to investigate how the mean cause the ball to accelerate, right?
I understand that, but this is a limitation that if you consider everything, then
Okay,
you
so
cannot consider everything in the theory.
I think that this part of the series is limited and it's not really practical for the real thing we're investigating here for this problem.
So what is your suggestion on improvements?
Maybe you can consider like how the external torque that would actually move the center mass works.
Oh, no. The center of mass will not move. The center of mass does not change unless the velocity of the ball is changed, or it is moved by an external force. The velocity of the ball does change, so the center of mass does change.
Okay, but you said that so what kind of, I think clear, like what kind of external torques do you consider and what kind do you not consider?
So the kind of torque that we consider are the torques that make a difference to the angular velocity of the ball. So any tangential component, so you have two balls, the top ball you can have a force that's going in that direction, in the each direction, and then that will cause the ball to spin faster. Any torque that causes the ball to spin faster, we will consider.
That causes the ball to spin faster, you consider.
And also gravitation.
But then you say that you don't consider the torque as I really can understand what's the classification here.
I'm sorry for the lack of clear explanation.
Okay, in my opinion, what you told me is that you only consider the forces that moves the balls like in a straight line.
No. The forces that causes the ball to spin. We do not consider the ball. The forces that causes the ball, the hurricane ball to move in a straight line.
Okay, so the forces that moves the center of mass is neglected.
Yes.
Okay. So, but I still think that this is still an it's still not
Okay, I understand why. I want to.
like maybe for example, in your experiment, do you see any effect that the center of mass of the variables actually moves?
Yes.
Yes.
Right, you want my explanation?
Yes.
Okay. So you know that at a slower velocity, the ball has a smaller angle, right?
Yes.
As the angular velocity increases, the angle will also change, right? That means the center of mass is lifted as the angular velocity increases. So yes, the center of mass definitely does. I'm very thankful of you for bringing that.
So okay. Let's go to the next topic. You said that the smaller the velocity is the smaller angle.
Yes.
I didn't see experimental data of that.
This matches to the angular velocity, matches to this point.
The x-axis is time. What does that mean?
So this is the angular velocity over.
But are you discussing about the theta, the median between theta and
I did not make an explicit graph on the data versus the angular velocity versus the angle, but this essentially relates that graph. So at a low angular velocity, you see a lower angle. At a higher angular velocity, you see a higher angle. At a even higher one, you see an even higher.
but that's only the qualitative data.
We can graph this out over. We can just change the axis here, and then you will have a
So
graph.
then I suggest that you do change the axis
Oh.
to show that your theory actually works in real life.
No, this can be graphed.
Yes, so I suggest that you do graph it.
Okay.
Okay.
Yes.
We talk about threshold omega, right? Threshold angular velocity.
Yes. Wait, did I talk about that? Yes, there is a threshold angular velocity.
What do you mean by that?
As your balls, actually no. Let's go back. Okay. As your air hits this ball, right? The ball will spin inevitably. The ball is also moving away from the width, right?
Yes.
So the faster the ball moves away from the width.
Okay,
So that's
please stop here. You said that balls move away, right?
yes.
So that causes center mass to move, right?
No.
Why? So it means that you only rotate and not.
Oh, yes, it does cause the center of mass to change. Our assumption is that that won't make that much of a difference to the net torque on the ball, so we're not considering that.
Okay,
That's one of our assumptions that we stated before.
Just continue.
Okay, so then when the wind goes onto this ball, the ball, what was that before?
When you talk about that the ball move.
Oh, the ball moves, right? The ball moves in the opposite direction of the wind, right?
Right.
Because the wind goes there and then the ball moves that way as well.
Yes.
So it's the same direction. So in the reference of the ball, the wind is actually getting slower, right? As it goes faster, the wind is getting slower. So we have to account for that when we do a force equation, because this is basically the force of drag, right? when you have a wind blowing onto a surface, there's a force on it.
And then how do you do this? Do a thing for this? How do you predict the effect of this?
Oh, so the ball moves away, and then you can find out the relative angular velocity of the ball, which is.
So we only consider that the velocity decreasing,
What do you mean velocity decreasing?
like the relative velocity between the holes and the wind.
We also consider drag force down there, and then rolling resistance in our model.
Okay, and what's the result that you get?
The result that we got was this graph.
Do you have experimental data that shows that it is correct?
No, we cannot confirm. We cannot accurately. We cannot accurately control our nozzle so that we can see such a trend, because the slight difference in angle can always contribute to a very drastic difference in torque. So we did not find a reliable way for us to test
Okay,
that.
and I think that this means that your theory for this is not practical, right? Since you can be done in real life.
There are ways to test this. We're just saying that with our equipment, we don't have the ability to test this.
So, but to me that it is still used as a prediction, since that you couldn't predict anything, actually predict anything.
Yes.
Okay, and
We're just saying that we don't have the equipment to do it.
okay, let's go back to the start. Okay, in the start you said that the vertical balls act like a gyroscope,
Yes.
but the gyroscope has its pivot point station, and the
We're saying that it's very similar. Just it's not a gyroscope.
Okay, so you just
We're saying
so
we're trying to.
you're not like making a serious discussion, like
We're trying to provide an intuitive explanation of how our function works. And so in fact,
okay. Okay. Another question: did the theta change even if the angular velocity doesn't change in your experiment? Does the theta varies up and down, or does it always stays the same?
initially when you spin it, there are some other torques that are on the ball, so the data may fluctuate. However, as the ball enters steady state, the data will remain relatively stable.
But to me, that's the problem statement said we should start the ball's rotation by using our hand, and then by pulling on it. And both of those actions causes immense amount of like the kind of unstable forces that you talked about. And so since that all those things acting on the balls can be predicted by your theory, how does your theory like where can you actually apply the theory to?
Sorry, I don't know how you can apply inputs on that. Actually, only predicts forces. When you spin it, you apply inputs.
Yes, so basically what I'm trying to say here is that too much unpredicted. Too much things that you didn't consider in your theory. That makes it unpractical.
You can't consider everything. This is in the start of the spinning. The ball is in a chaotic system, so it's very hard to predict anything. It's like trying to predict turbulence. You need a lot of computer modeling. It's not practical.
To me, that you're just making some useless predictions and that.
Okay, thanks up for the discussion. And one of you is summarize the discussion.
Okay, here's my summary. Okay, the reporters before only considered the external forces and force that doesn't move the single mass of the ripples, which to me seems too ideal and not practical. I think that he can show that his theory can predict anything in real life, and that he didn't find reliable ways to maintain the wind speed that he might as he has assumed in his theory to be stable, but that is probably not the case in the real life. So I think that his theory lacks a lot on this part, and he doesn't have
thank you for the summary. So now is question from the reviewer.
So, let me turn to the page 16. So, did you make this board check that is stable enough for you to do the experiment?
This is not actually our experimental setup. This is just a model of algorithms. In this case, we are actually trying to set up something called shearing image. So we're trying to see the airflow around there to try to predict turbulent effects using a parabolic mirror. But this is not our actual tabletop that we use. It was a black tabletop that is stable.
And as the opponent asked, I just want to confirm that you suggest that the force that wind blows will not make the center of mass to move in your all theory assumption, and you use it in your experiment analysis.
I think we said, I assume that the force, when if a external torque is applied and moves the ball, then it will be negative.
So, do you think that if we conclude that the force will make the center of mass move, that it can make the result more better?
You mean like if we consider the torque that makes the center mass move?
Yes.
Yes, definitely. And I think that's the most important part that the torque didn't discuss about.
Oh.
Yes.
Mine also included. I do not think that it will make a noticeable difference because a translational force will not cause a torque on the system. So the angular velocity should not change too much even if you have a translational force.
So you have suggestions if you include that force made the center of mass move, and how can you calculate the movement and to divide it from the
To
rotation?
me, the easiest way to put it is to just calculate the torque, like the friction and how the torque from the wings to affect the bones. And to addition to what the proposal said, he said that the translation of the protocols with the measurement, but we didn't consider that the bigger balls center mass can move up and down as well. Yes, yes.
Okay, time's up. Thank you. So 2 minutes for the reviewer to prepare your review.
And now I'm going to make a review of the problem 6, hurricane ball. And this problem is about 2 steel balls that can be spun by hand and wind blowing, and it will stand up and spin at last. So we should explain it. And I'll make a summary and comment of the reporter. First, he told us about the theory procession, and he made a torque analysis and angular velocity analysis. And he made quite good at the field diagram, and we can know this analysis clearly. And then is the setup. Use steel balls and the laser tachometer to made up his experiment. And then the parameters are the ball size and the growing strength. And about the experiment, he observed the spinning of the hurricane ball. And it's good that they control the blowing force. That is a really good point at this problem. And about the results, they suggest that blowing time longer and the angular velocity will be bigger. And I think although they made a clearly explanation of the theory, they still can be more familiar with the procession of the equation part, and that will be better in the performance. And we also suggest that their experiment can be more clearly with the theory. And we also think that you can do more experiments in this section. And comments of the report, the advantage is they made a good explaining of the problem, and we suggest that they lost some units in the picture, and that's a small problem. Just don't mind it at all. And as I said, you can be more familiar with the theory part. It might be better. And next, I'm going to make a summary of the opponent. The advantage is they catch the most important problem, that is, if the force will make the center of mass move. And suggestions is just they can be more focusing on the drag force, which is very important too. And about the discussion, they asked that if these two velocities are the same, and they replied that they don't have data, but they are the same. I think that you should have experiment data that will be more concrete to prove this, not just using the essays to prove the two velocity are the same. And they asked that did the wind make the ball move, which is a very great question, and the reporter said that they didn't really move, so I think they should consider that too. So about the review,
Okay, hands up. So it's time for the concluding remarks from the reporter.
So for the experimental data, the orange, I may have not specified that the orange points are in fact theoretical data points. The orange points here are theoretical data points. Okay? Then after you fit it with the ground effect and Lattice effect, orange points are data points. Okay, second point is that we do not assume that the air will not displace the ball. fact we do. The ball will definitely be displaced by the wind. But we're saying that it does not contribute a noticeable torque to when the wind displaces the ball, the force component is not going to contribute a massive amount of torque. However, the wind itself will. And also, in the point of drag force, we definitely consider drag force. The term here is considering drag force. Is derived from the drag equation, and air friction, that's drag force. Yeah, we definitely consider drag force. That's under my
Thank you. So it's time for the question from the jury. Jury has some question.
I would like to know what is your own contribution. I mean, for example, your team.
Okay. My contribution, the entire thing.
Yeah, for the entire team. The entire world.
This entire thing is something I made myself.
Okay, so you derive it?
Yes, I derive everything. In the research paper, the steady state here, this thing is also shown in some other research papers, but they used the Lagrangians to derive this. I did not use that. This is all myself. I did all that theory. This is all original.
A question for the reporter. So, when you plot the parameters like the angular velocity versus time, something like that, I was wondering if you are whether you were constantly blowing the air on the ball or not.
Oh, sorry.
It's after the blow or during
There's no air blowing here. We're just trying to see how the ball slows down.
So in the experiment, when you try to introduce the air blow, so how long do you introduce that? Like for how long?
Until it
A
reaches.
short pause or is it a short pause of the air blow or it's a constant flow of air?
We introduce a constant flow of air until it reaches a maximum velocity, threshold velocity.
And then so the plot, okay.
Here is the maximum velocity it came back. The wind velocity. Graphing the maximum velocity possible, and we can blow the air over. Yeah. So let's say we have a wind.
So that's why you presented a maximum, like a threshold velocity?
Yes.
That's okay.
Like the maximum angular velocity achieved by a certain wind velocity. Yes.
Yeah, you may have a short question about the reporting. Can you distinguish the major resist either from the friction or the
Loading resistance?
The major resistance is the air drag or the rolling resist? Which one is the major one?
So, judging from this, from our simulation, from the experience of the simulation, we know that if there is a drag force, then there will be high force here that slows down. There will be a very high amount of force that will slow the ball down when the angular velocity is high. And then when the angular velocity is low, there will be little force stopping it down. So if the drag force is the main thing that's stopping it, then the graph should look something like this. However, that's not the case. The graph actually looks linear. That means a roughly constant force is being applied onto the ball. From this, we can conclude that the rolling resistance is the primary force that's on this in our experiment.
Okay, thank you. A short question for the panel. So what do you think is the key missing point in the report?
Then we ran into many important forces towards acting on the balls. And it could show that part of most of his data. I think most of his series really shows that the data actually matches his data.
The reviewer agree?
I think the most important point is we should do more experiment on a theory, and you can prove it or tell us where the theory is wrong or something else that you may have experiment to prove something you can
Okay, thank you all. And let's have
Yeah. So, what's the rule for the incredibly high frequency of the speed?
Okay. Let's go back to so if incredibly in order for cosine of theta here to be positive, you need a high enough frequency. So that 2/5 minus g divided by angular velocity squared times r is not negative. Because if it's negative, then your angle is negative, which will not make sense. In this case, so the high frequency allows it to be in a steady state. If your velocity is not high enough, ball will not go into an angle.
The question is, what's the main cause which lead to the incredibly high speed of the ball? What's the main cause? The main reason?
Short radius high force. You have a large force on the ball, but you only have a little radius. That means you have.
So the small, to reach a high speed, you want the smallest ball, as small as possible. That's what you mean.
Not really. It depends on how the let's say it depends on how much. Wait, are you asking can you restate the question?
If you want to reach a higher speed,
Yes.
what would you do?
Increase the wind velocity.
Okay. Do you have a video of your ball moving? Spinning?
We may have.
That's okay. I think this time is.
I have a video here.
Okay, thank you. So let's give some time for the jury to
Check with their score.
we are ready. So now let's first show the score for the reporter. Okay, so it's 6, 7, 8, 7, 6. Okay, now let's show the score for the opponent. Eight, 8, 6, 6, 6. So now let's show the score for the reviewer. 7, 8, 4, 5, 5. Okay, thank you for the jury and thank you for all the okay. So let's have a 10 minutes break. And in the meantime, let's switch position for the opponent on my left hand, reporter on my right hand, and the reviewer in the same hand. So it is ready, so let's have our opponent challenge.
Problem 8, Sci-Fi song.
Number 8, Sci-Fi song. What's your decision?
We accept.
Accept it. The challenge accepted. So 5 minutes preparation time for the reporter. So please write down the remaining presenter's name on the check form.
传导一些
Okay, recorder can you go, please?
Honorable judges, ladies and gentlemen, good evening. I'm the reporter of The Miracle, and today I would like to report problem number 8, Sci-Fi fact. First, here is a problem description. Tapping a helical spring can make a sound like laser shot in a science fiction movie. Investigate and explain the phenomenon. First, we have to define what is a laser shot sound. So, we actually did some acoustic analyze with audacity and discovered that the frequency diagram has some slope, and we considered it as sci-fi sound. Here's our outline. First, we're going to discuss about the phenomenon. Then the body is about the dispersion relation and about other parameters. Last, we have the conclusion. First, we have to analyze the sounds from the spring. First of all, we have coil collides, that two circles of the spring collides. And this sound quickly damped, so we don't think it is the main sound that we hear, the laser shot sound that we want to analyze. And if we don't contact between coils, then we have a reverberation, which we call Sci-Fi sound. It's like these slopes. And here's a phenomenon. First, when we tap the spring, the sound, the velocity depends on the frequency, and this is so-called dispersion. So, when the sound wave goes by, then we have a higher frequency sound and lower frequency sound. But due to dispersion, the higher frequency sound will run faster than the lower frequency sound. So, as you can see, this yellow line means time, and this is our frequency. This yellow line goes here, and we met the high frequency, which calls a peak. Then the higher frequency touches the wall and then goes back. And goes back again. So here we detected another peak, and this is a period. Here is our setup. This long line is our spring, and these are our stacks. And this is a pendulum that we used to hit the spring. And here we glue on the metal. So this is we can see it as a wall. And then another side, we have a microphone to record sounds and analyze by audacity. now we have a lot of kinds of helical springs. First, this is type 1 and type 2. And then this is normal springs, and this is just different types, yeah. And this is slinky toy that you have some springs and it claims that it can walk down the stairs by itself. And we call it type 3 and type 4. Actually, these coils have thickness, so we have an L, we call it uncoiled length. And we can calculate it or just measure it, yes. And this is our experiment data. This is the period that I claimed before, and this is the time, the period time, and this is our frequency. As the frequency goes higher and higher, we got the period got decreased with power relations. And these are different kinds of helical springs, all react the same. And then here are another parameter that we tap. It's a tapping position. As you can see, if we tap here, then a sound is emitted and it's transferred like this. So actually, we have different periods because we have a sound wave that goes here. And another sound wave, if our detector is placed here, then we have another sound wave which travels first to the wall and then reflects to the outdoor side. So we have two kinds of periods for every frequency. And then we can have a ratio. We can have a ratio that means that this is a frequency. Sorry. This is a period between these two sounds, which T prom means from the tap point to the wall and reflects back to the sensor. And T means from the tap point directly to the sensor. And we calculated that from the tap point, if there's a P, then we calculated what the P would be in every situation. And then we discovered that it fits. It fits very well. And here are other parameters. While we have a string, then we have its uncoiled length. Uncoiled length. Then imagine that if a spring is lengthened, then the sound emits, then it travels by the string itself, but not like this. It travels like turning around, right? Because it has to travel on the string. So actually, we have to do about the uncoiled length and the period, while it is a parameter that we have to discuss about. And we started to after we did some experiments, we discovered that it fits our theory that it's pretty linear. It fits very well. And another kind is tension. That when you pull the string itself, it lengthens, and when the tension varies, the length varies too. But the uncoiled length doesn't vary. We did some tension and period experiments too, and we discovered that there are no relations, obviously. So this is another evidence that tells us that what really matters is the uncoiled length. The sound is traveled on the steel string, but not on the string itself. Here is our conclusion. First, we discovered that Sci-Fi sound is caused by dispersion relation. First, this is a long wire. When this is a long wire, we emit a sound, then the frequencies differ. Then it causes a dispersion. And in normal situations, we hit a sound like this. It just goes, it didn't have a very obvious dispersion phenomenon, so we can't detect it that there is a Sci-Fi sound, while Sci-Fi sound is caused by these slopes that is by dispersion by frequencies. So according to this conclusion, we can not only use string, but very long steel wire. If we use very long steel wire, then we can also treat it as a very high tension string or something else. And we can predict it that it has the same phenomenon. But actually, if you use a string, then you can collide very lots of steel wires into a very short distance, causing these phenomena more obviously. So that's why we have a Sci-Fi sound in spring, but not in normal strings. Oops, sorry. Please. Oops. Oh, okay.
One
Harder. The last page. Thank you. And then we have reverberation. First, the sound should be low damping, because if the sound has a higher damping, it decays very fastly, and we can't detect it a Sci-Fi sound while the sound needs to travel for a long distance. And while in streamlines we have low damping, so we can detect this phenomena obviously. Just imagine another airline. I mean a line made of air. Because its damping is very large, so if I speak to you, then you didn't hear any Sci-Fi sound because it didn't have a. It's not because there's a obvious dispersion, but it's because it's damping. Yeah, and we have to reflect the sound, or we can't do a very beautiful periodic sound, and so we have only a very. If there is no reflection, there will be just a very, and that's it. So without reflection and without Sci-Fi sound, it's because dispersion and reverberation. And the dispersion is depending on the radius of core and the wire. It is some special. It's a parent. The radius and the coil is a parameter of the sound of the sound wave. So it also occurs. Yes, and that's my report. Thank you.
Okay.
I have some questions about the report. Just how close do you have the Hilton speed?
You mean the tools?
Yes.
I have we use a little pendulum, like this. Yeah.
Oh, okay.
Because we don't consider it a very important parameters.
So do you change the microphone position in all your experience? Because you means that have dispersion, right?
Dispersion, yes.
So do you change the microphone position?
No, but we change the position we tap. I think it's related.
Do you do a expand or vertically?
Pardon?
Just vertically.
Vertical?
Yes.
What do you mean vertically?
Just you that the Hilton speed drop down by nature.
Oh, you mean the spring just dropped down by natural? Yes. We didn't do it, but actually, we think it can have a we didn't did it quantitative, but it did have the same phenomenon. And it is more complex, while another kind of boundary is not very predictable, or we can't actually control another kind.
Another question is how close to analyze the sound?
Audacity. The software.
Do you use STFT to analyze or other things?
Yes, Audacity uses FFT.
You use FFT?
Yes, fast Fourier transform.
So how long you use the FFT in your sound?
What do you mean?
Because the FFT is a short time you analyze the sound of all the frequencies. So how short do you use? You mean the density or the length of the record?
Okay, thanks, Nat. So, 2 minutes for the comment to prepare.
Then I will pick 4 of the report. Just he used different frequency to draw the experience and have the results of the Sci-Fi sound. But I think that the Sci-Fi sound is a little the same and all your experience. That maybe the same Sci-Fi sound all in your experience. So maybe you can change the other variables and will change the different Sci-Fi sound on it. Then you expand the theory is an expression of the sound of it. But okay, then problem number 8 is Sci-Fi sound. That is having a good list that will have a little sound of Sci-Fi sound, like the Sci-Fi sound. And you use a theory just like sound diffusion and FFT to analyze your sound of it. And you set up a slinky and tempo and the pendulum to have the sequence speed. But you didn't change the different tools to whether it will have a different Sci-Fi sound of it. Maybe it will change of the Sci-Fi sound. And then you change the different take place, but you didn't change the microphone of the microphone position. Maybe because you said that is a dispersion. So the microphone position is the most important thing that because the Sci-Fi sound change on it, so it is important, but you didn't did on your expense. And just you have to the lens and you have a really clear pic to tell us that it's Sci-Fi sound on it. And if the code you tell us that the code didn't connect to each other, it didn't have a Sci-Fi sound, but it didn't connect, it will have a Sci-Fi sound. And you have a clear position and well explained of the theories to have let us know that the dispersion is the main focus on this problem. And you just use you do good at the 12 of analyze. Just use FFT and let us know that the 12 frequencies. Let the frequencies of the Sci-Fi sound go. We found the high frequencies to the low frequencies. Then but that is you didn't just know that because you use the horizontally, but you say that the code didn't connect will have a Sci-Fi sound. But even you tap it, it will have a little connect at all of the code. So maybe you didn't consider that the oscillation of the Sci-Fi sound. Just and you use a microphone to record the sound of the Sci-Fi sound. But how do you avoid that other sound outside, or maybe you tap is that sound? You didn't. How do you didn't tell us how to avoid that the tap sound or the tap sound? Just maybe the tap of the pendulum will have a sound that will affect the Sci-Fi sound you as well. So because you said you FFT. FFT is a little time and you analyze the frequencies, how much in it. Maybe you tap you use the tools tap the frequency. That frequencies will in your result. It will affect all your results and your conclusion. Okay. So can just let us because so just so that you use horizontally. Maybe you can next time you use vertically that, and maybe you will have a Sci-Fi sound that you can try it. How do you think that if the frequency is vertically?
Actually, I think it because when you didn't stick another boundary of the spring, that these two kind of boundary is different about that. When a wave as like this collides with a wall or a free boundary, it reacts different. So I think that, but that's only about the phase of the sound. So I don't think that if we use horizontally, that the Sci-Fi sound will vary a lot. But it will vary. But if we use horizontally, I think we have to analyze more, and it's more complex.
You use horizontally. That the pole on the natural land will connect each other, right?
Pardon?
Yes. Because your natural let the horizontal frequency down.
Yes.
Yes. The length of the pole will connect to each other. So how do you think that what didn't have a Sci-Fi sound will have a Sci-Fi sound on it?
May I use the backboard?
Sure.
Thank you. So you mean this is the floor?
Yes.
And this is my spring.
Yes.
And it becomes like this.
Yes. Yes.
Yeah. So how about I can treat this as a wall while it is very dense, right?
Yes.
So I consider that Sci-Fi sound is caused by this wall.
Oh.
If I use vertical.
So it means that this house didn't have the Sci-Fi sound, right?
Actually, that we know that Sci-Fi sound is because dispersion.
Yes.
So I think I claim that everything, if this what we use spring is just to make that the phenomenon more obvious, because dispersion is everywhere. Right. So I think if you're gonna ask if there is a Sci-Fi sound, I'm gonna answer yes, but very small too small to detect.
Another question is, you say that the dispersion and you change the different place you have it. Like this, you have it here and you have it here. You mean that. Then you record the Sci-Fi sound. If it change, because the dispersion, then the different length will have a different Sci-Fi sound in your by the dispersion.
So this is our analysis when we did different tapping points. Yes. And as you can see, when we change the tapping point, the Sci-Fi sound changes and the slope changes. That's right. Yes. The slope changes, so the Sci-Fi sound changes.
So how change? Just more clearly will have more people other things.
Pardon?
Just part change.
What do you mean what change?
Just you change the different pace of having.
Yes.
And parts happen.
The period changes.
Yes.
The position changes, right? So the period changes, and the period ratio also changes. This two slope is in the same frequency, but there it is. This is a bigger T and this is smaller T. Because I claimed before this one travel path is here and another is here. So there has a little bit differences. And if I change this kind, like my tapping point, this also changes.
So
The period also changes, while the distance from the tap point to the microphone changes.
so it means that the two peak of the Sci-Fi sound will change it.
What do you mean the two peak of the Sci-Fi sound?
Because you want to have two peak on it. Just so there is one peak of the Sci-Fi sound, and there is the other peak.
Yes.
So it means if you tap at a different pace, the two peak length will be changed by.
I mean the period between the peak changes.
Yes.
Not the peak itself
Oh
changes.
yes, the period changes. It means that.
Yes, the period between the
Oh.
peak changes.
And another thing is this all the picture you use FFT to analyze?
Of course.
So, but I know that FFT is that have little times, and that we analyze the frequencies of it. Just FFT is like this, and that have different frequencies and the body, and maybe you will have one peak at here, another peak at here, another peak at
Of
here.
course.
So how can you use FFT to do that features? Because there is a little peak, but there is hidden time on it.
Oh, you mean there's no time
Yes.
on my diagram, right? So actually, how about this? This is a wave.
Yes.
In a very short time. And in this very short time, I do FFT.
Yes.
And it becomes like this. Anyway.
Yes.
So I plot it, not like this two dimension, but like really like vertically. So I tackle the peak. And I pick the peak. And in this kind, it seems like this.
Yes.
So in this kind, the peak is like this.
Another question is how long does the FFT choose? A little time.
Actually, because we kind of trust the software. So we didn't change a lot of the settings inside.
Because we know that we errors like will have the things like STFT will have the different times that is 0.1 second. So we can hear the different frequencies that the Sci-Fi sound is. So maybe if you change the FFT sound, FFT, that will have some change on it.
I don't think so. While if I make this bigger, the frequency still remains. The wave is just act like this, and the frequency is just remains. And your wave package that you want is still inside. And other thing that there's something here. So if this becomes bigger, then
The main frequencies will now change.
what do you mean?
The main frequencies didn't change.
I don't think that it changed a lot.
Oh.
Except you did like whole, very crazy logic. Or I don't think it changed a lot.
And that's, I think that all the peak from high frequency to low frequency is the same. So is that the same Sci-Fi sound?
What do you mean?
Yes, because it at your pictures like this, and two peaks, right?
Yes.
And is this frequency sound is the same to this?
What do you mean this frequency?
Just you hear it or analyze it. Just this frequency, this Sci-Fi sound is the same to this one.
Yes.
And so okay, so all your explain that the Sci-Fi sound actually is the same.
No, sorry, I have to fix that a little bit. I thought your saying is a it's a frequency thing or something else.
Oh.
If you're gonna say the slope
Yes.
itself, these slopes are different
Oh.
because I can see that low frequency walks slower,
Yes.
so it has more time from here to here, and for high frequency it's fast. So it becomes like this and this and this and so on. So on.
Then another thing is why you have 2 peaks, not 3 peaks or 4 peaks?
Second please. This is a string.
Yes.
Assuming that we detect it. This is the sound.
Yes.
This is another.
Yes.
There,
But maybe it will go back and go back again.
then you got another period, right?
Yes.
Because the sound from here to here and then to here is stable.
Yes.
So you got like this, and after T, you got like this. So that's why there's a big
But
gap, right?
you means that if I tap it right here, and the frequency will, Sci-Fi sound will from here to speed out, and here to speed out. Then, why you didn't hear it? Because the sound is, the dispersion is that here have a high frequencies and a low frequencies, but it's near, so we cannot know it's a lot of difference. But at here, the high frequencies is a lot is transfer slower than a low it's better than a low frequency, so we can hear the difference. But if he just the sound transfer from here to here, it will have a lot of Sci-Fi sound on it.
What do you mean a lot of
Because
Sci-Fi sound?
it means that here you will have one Sci-Fi sound, but it's not really here. At
Okay,
here,
can I
another
start the
Sci-Fi.
discussion? The opponent make a summary, please.
It is tell us that you think that the vertical experiment maybe will the same result on this because that at the natural frequency built down the last flow will the same will not have a Sci-Fi sound. So the main Sci-Fi sound is that the flow didn't connect to each other, and he tells us that the main focus of the Sci-Fi sound is dispersion, and it will have only this. You have two peak Sci-Fi sound, just one peak and two peak by the transfer to one to top to down, to top from this way to that way, and says and the pulse will change when the tap frequencies The parent will change when tab of different
Okay, thank you
positions.
for the summary. So it's time for the reviewer to have questions.
Great. So my first question for the reporter, can you go to slide 14, please?
Slide 14, please.
Oh yes, right here.
Oh, yeah.
Can you explain the circular graphs on the bottom, or the circular shapes on the bottom?
We mean things like that.
Yes. Or like why do those occur, or what do those mean in terms of the experiment?
I think it's a little bit like another kind of dispersion, because yeah, it goes another kind of dispersion. While in these frequencies, it goes another kind. It reacts another kind of period.
So is there a reason you only analyze this type of slope and not the curves at the bottom?
The curves at the bottom is a little bit more complex, but we can't actually catch what is another kind of dispersion. We can't catch it very clearly. So, and these data are there. Yeah, it's clear and you can analyze it. And these are, it's mess. We can't really distinguish it.
And another question, you say that the high frequencies inside the spring will travel faster than the low frequencies, right?
Yes.
Is there a reason that the high frequencies travel faster?
While the sound speed is focal dispersion, while the sound speed is related to the frequency itself.
Do you have something that explains why it travels faster?
Do you mean like physics series?
Yeah, or maybe like a model or like an equation that represents it?
For a second, please. This is what we found from papers. Yeah, and I wouldn't say too much here about is our others research results, but as you can see in here we got this is the speed of the sound and this is the frequency, and we can got a kind of relationship between the speed and the frequency, and this also explains that the strange sci-fi sound below you just discussed about, but this is another kind of frequency, another kind of speed.
So just now the opponent asked that the time frame can affect your result because you're using, like if you're using FT versus STFT, right? But, and then you said that it doesn't matter. So I think that when the frequencies are dropping very quickly, the FFT can be shifted as opposed to an STFT that wouldn't. So why did you choose an FFT instead of an STFT?
FFT is faster and it's within just little time, and within
Okay,
I don't
time stop. So 2 minutes for preparation for the reviewer. Okay, review your time flow, please.
Okay, so now I'll be giving the review for undertone sounds. Question number. Okay, so the problem statement is that tapping a helical string can make a laser shot sound like in a sci-fi movie, and investigate this phenomenon. So first I'll go over the reporter. The reporter first talked about how the colliding of the coils is not a very big factor in this experiment because the colliding sounds dampen very quickly, so they aren't very noticeable. And second, they talked about that the velocity that the sounds travel through the spring depends on the frequency of the actual waves that are traveling, and their theory says that there are two periods for every frequency because one goes directly to the microphone and one bounces to the end and then bounces back. And in their experiment, they did sideways spring instead of a vertical spring. And they said that different types of springs all have the same result, and there's no correlation for the tension of the spring, but there is a correlation for the coil length of the spring because the sound actually travels through the coils instead of just through the air between the microphone and the coils. And the conclusion is that this sci-fi sound is caused by dispersion and reflection, and that the dispersion depends on the radius of the coil. Some good things that the reporter did were that they had very clear graphs. There was no really noise except for the bottom circular kind of shapes, and the phenomenon explanation was very good. Some things that I think they could have improved on were that there was not really a model to match their data, or like some clear equations to explain their phenomenon. Right, for the opponent's report, they said that their microphone position was the most important, and then that the type of tapping, like whether you used a hard or a soft object, did not matter. And then their main point of argument was that there's a difference between STFT and FFT, and that the reporter should have used STFT as opposed to FFT because of the short duration of the sound. I think that type of tapping does matter because, like, if you use a pendulum, you might hit it once, or there's a difference between whether the pendulum just goes to the coil and collides and then stops there, or if it just taps it and stays there. Something I think the opponent could have also touched on is that the fact that the reporter only used a pendulum to hit it sideways, so it only sent transverse waves through the spring. But I think that they could have also tried longitudinal waves, so if the coil's this way, you hit it this way and it sent longitudinal waves through the spring. And during the discussion, the opponent asked that, should we be using, or did you try experimenting with vertical spring? And the reporter said that it is more complex if the spring is vertical due to the bottom being open. And then I think that another reason they shouldn't have done that is because the coils.
Thank you for the review. So now there's 2 minutes for the reporter to conclude.
This is a problem of the sci-fi sound. And first of all, we know that when a sci-fi sound is occurred, it's because dispersion and reverberation. And we discussed about with the opponent that if we place our spring vertical instead of horizontal, then we didn't think that first we have to claim that tension doesn't matter. But it would, because of vertical boundary, we think that it would be more complex. But it would. We don't think that the data would vary very much. And I still can't understand what the opponent means many sci-fi sounds. And it's a safe way traveling down the spring if we, no matter how we equalize it, right? So actually, we think that we did the experiment, but we didn't show it. I'm sorry for that. And we also discussed about the FFT and STFT, and the problem with, I think that this we can actually, because we are just capturing the frequencies in every time. So I don't really think that this kind of analysis skills really affects a lot, because it's just an analyzed methods. The facts is there, so the analyzed methods should come out with similar results. Yes, and this is problem number 8, Sci-Fi sound, and thank you.
Okay, thank you. Any questions? Any questions from the jury?
So you are saying you do FFT instead of SDFT. Okay, so in your microphone you only have a 1D data, right? And then you do FFT. And how come you have 2D data? Two-dimensional data. I mean, in your figure, you have 2 dimensions.
That's not 2 dimension. That's one of the axes is time, and another axis is frequency. So we record for time, and in every time we have a sound and we have a frequency.
True, but because now you have 2-dimensional image, right? That means at a single time,
Yes.
you have lot of frequency.
Yeah, so we're finding a peak.
Finding the peak.
Yes. There are lots of frequencies, but one of them has a master volume.
So what's your sampling period?
Excuse me?
Sampling rate?
Sampling.
Sampling rate.
Sampling rate.
Can you go back to your image?
Please, reviewers, thank you. Please, possibly have to. Yes, I got it.
Okay, maybe I remember it's page 14. So
Yes. 14.
yes. So this, for example, you have let's go through this line. For example, at time equal to 0.4 seconds.
Yes.
Okay, so you have lot of frequencies,
Yes.
right?
Yes.
So why you have lot of frequencies? Because you only have, I mean, you only have a one-dimensional signal,
Yes.
right? Then how come you generate this 2-dimensional image?
And this is time.
Yes.
So in every time that a sound comes in the microphone, and this sound is combined with a lot of kind of frequencies.
Okay.
And these frequencies are shown in
Oh, I
this
see.
very
Okay.
thin.
Okay, I got it. Okay. So you, in your model, have you explained why this line is like a hyperbolic line?
No.
It's definitely not a equally sloped line, right?
Yeah.
So you, in your theory, you cannot see this, right? You cannot tell why this is.
We can tell it's divergent. It's because this dispersion, but while the dispersion theory is quite hard to practice.
Could you define dispersion?
Dispersion?
What does it mean?
Different frequency sounds travels different. The speed of different frequencies have a different traveling speed.
Along the spring or in the air?
In this situation, along the spring.
Can you turn back to page 14, please?
14, thank you.
Okay, can you just explain easily, simply, like for k equal 1/2 and k equal 1? What does that tell you?
You mean in
K equal 1/2 and k equal 1. What tells us about these two factors?
Okay, K means that tapping position ratio. So when when the k becomes a half, that means that approximately we have from here, because we know that the sound emits from travels here and then here. So we can do this ratio, this to over this. And this is our k. So if our k is bigger, then it means that this and this is more similar. So if the k equals 1, that means we hit here. Because this and this is the same. And k equals 1 over 6 is like very close to here. While this is 6 times of this.
Okay, but from your the both pictures, does it show what you just said?
What do you mean?
For the k equal 1/2, right? You have so many, like for different times, you have so many frequencies
Yes.
layer.
Yes.
And actually, for k equal 1/6 or 1/3, you can see clearly there are like a double lines there. But
Yes.
for the other, like k and 1/2, k and 1, there are no double lines.
Yes.
So is that really is the right? Is this right from your theory?
Yes. Well, when k equals a half and 2, that means a sound emits from here, right? And then like this. But and this is 2 times of this. So after this sound arrives, then let's assume this from here to here, the sound needs time t. So from here, over here to here needs 2t. 2 times t, right? Because I said that the k is, this distance is 2 times here. While k is 2 times, right? So actually,
K equal 1/2, the distance 3 times, right? It travels 3 times the distance.
what do you mean? What do you mean? I mean,
You just go directly from the middle point to the microphone is 1/2 of the length, right? But if you go to this way and then go back, it's 3 times of the half. That's what I mean, the half length.
yes.
Okay, never mind. Okay.
Well, I guess 1/2 is not here, right? 1/2 maybe.
Yeah, when yeah, that's some misunderstanding. Well, I mean 1/2 is this, and this
The whole length.
ratio is 1/2, not this to here.
Okay.
I'd like to go back to this dispersion.
This version.
So, from which part of your data can you conclude that the speed depends on the frequency?
Actually, when we look at the experiments, we can, I mean that this is the time,
Yes.
and this is the frequency.
And
So in every frequency, that like this frequency it travels here to the microphone. While it is like a peak traveling. So it travels time like this, but in lower frequencies it travels like this, longer time.
can you hear the laser shot noise with your human ears?
Yes.
But you are talking about but you just said that the dispersion you are talking about is the speed along the string, not in the air. But we can hear it, so
We can think that when a peak arrives a point, then it emits a little bit sound out.
okay.
Right. So in the position, with different frequencies, arrives times is different. So you hear like ding.
Okay, thank you for the answer. So, let's jury calculate this score. score for the reporter first. Nine, 8, 7, 7, 7. So now show the score for the opponent. 8, 7, 7, 6, 6. So that's showing the score for the reviewer. 7, 7, 6, 6, 6. Okay, thank you. So now let's make a 10 minutes break. Okay. And in the meantime, we change the position. So opponent ready to change. Question 4, funnel and ball. Rejected. Opponent, please change again.
Soy sauce optics. Oh, I'll remove that.
Carbon 9 soy sauce object.
Yeah, 9.
Reject.
Rejected.
Moving pendulum.
Carbon 14, moving pendulum. Accepted. So we have 5 minutes for the reporter to prepare. So please write down the main presenter's name on the blackboard.
个系统里，啊不，这个不要理它，这个有就好，就这样子。可是这个我在系统里。多了麦克风，不对，这个系统多了麦克风，但是这个系统是正确的，所以这个系统多了麦克风少了，就是所以刚刚是觉得我这个状况在刚好，以这个为准，这个为准，对，谢谢。
Good evening. I'm the reporter from team funding on the problem 14 Division. And this is my report online. And first, I'll make an introduction of my report, including the problem statement and our first look at the phenomena. And we will make a theory approach of my problem, and I'll make an experiment and simulation, and see if the simulation will fit my experiment. And at the end of the report, I will make a further discussion, like looking some interesting motion in this problem, and I'll do a conclusion. Okay, first, let's look at the problem statements. And problem statement said we will connect two objects, and one is heavier, one is lighter. And we place it over a horizontal road, and when we release the lighter load, it will spin around the rock. Keep the heavier load falling to the ground, and the power statement one way to investigate this phenomenon. And this is the observation video. Okay, and if we show the motion of the lighter load as a figure, we can see the pattern like a spiral there. And next, these two video is the motion of heavier load. And you can see this, we can depart the motion of the heavier load into two parts. One is the falling part and one is steady part. And the upper video is the falling part, and it means the heavier loads will falling, and the stationary part is mean it will stop. Okay. And then going to the theory part. And first we'll introduce the Capstan equation. We can calculate the tension force between two in upsides, and we all know the normal force on the rod. So the derivation can easily get with simply for analysis. So I just took the note, and we just go into the paper. And before we analysis, we will talk about the Edward machine. And first, we can look at the Edward machine. You can see this tension force and the gravity force, and including the friction force on the rod. And the friction on the rod, we can use the Capstan equation to calculate. So we just express the tension force like this. Now we can get the acceleration of the Edward machine. And this for analysis of the river pendulum. We can analysis the problem by a coordinate system, and we can get coordinates like this, and we can get a velocity and the acceleration like this. And next, we will do another forward analysis on the problem, and we can see for the heavier load is I call it or call M1, and we can express the M1 equation like this, and this motion of M2 equation in two different directions, and because the length of rope is constant, so we can write this equation like this. Okay, so if the heavier load is falling, I call this the velocity is bigger than 0. So we can get these two equations by this equation. So we can use the numerical solution to calculate to solve our problem. So, but before our calculate on the problem, we need to know the kinetic coefficient of the kinetic friction. It's mean mu, and we use two load is different mass, and use tracker to analyze this. Okay, and we can see the y here, and if we put it into the Python and make a 3D, we can get acceleration. And this equation is like the Edward machine. Yeah, and we can use the equation to find the mu, and we use this equation. So we get the mu equal to 0.2189 in my experiment. So let's go to the simulation. So I use the numerical solution to solve my problem. So you can see this is the motion of the heavier load, and this is a simulation figure. So you can see maybe this is not okay. So I will make a compare with the simulation experiment later. And this is the lighter load motion. So you can see the pattern will look like this. And this is a simulation and an experiment. You can see there's experiment line and a simulation line here. And you can see it's worked very well. And this this is the simulation animation. And let's go to the, our experiment part. And there was some parameters were discussed in this part, and like different mass, but in the same ratio, like 2 to 4 or 3 to 6, and the length of rope, the mass ratio, and the differential angle. And this the equation of the code, just like the last next page. And let's look at the different mass in our experiment. Okay, and this result of the experiment. We can see if we use the numerical solution to solve the problem, the simulation should be at the same point, and the y-axis is displacement of the heavier load, and the x-axis is the mass, and we can see if the mass is 1 to 7, it become is 4 more smaller, and I got the conclusion is if M1 gets heavier, the displacement of M1 will get bigger also. So, but we can see there the displacement of the one is keep decreasing. So I think that it may be a air resistant effect, and there's a experiment of mass ratio. Okay, we can get this picture by the experiment, and I just say the conclusion. In these cases, we can get when the mass ratio is in 1 to 4, 1 to 5, 1 to 6, 1 and 1 to 8, 1 to 10, and 1 to 15. We can get the mass ratio can be the Fiona can be the catalyst. This means the lighter load will spin more circle. And this is the experiment of the lighter rod. There's a rod. Okay, and we can see there's a figure of our experiment. So we can clearly see this picture, and so our conclusion is the length is longer and the displacement is longer. And I see a interesting data in this, and the displacement and the length of rope ratio were close to 0.1, and this is a differential angle. And we can see this figure, and it so we can see this figure and find the conclusion is in this case we can find the ST grid have a best looping pendulum. So let's look at some interesting motion I find in this problem. We can see this video. Okay, you can see the heavier load was fall and make a brief stop and fall again. So we make the motion of F1 into this picture. We can see it's fall and stop again and fall. Regarding to this problem, we can describe it as just in the beginning the tension force 2 were smaller than tension force 1, but in some special situation the tension force 2 were bigger than tension 1, and the heavier load will make a brief stop, and at a short time again it will tension 1 will be bigger than tension 2. And I'll make a conclusion. And you can see in the beginning of our reports, we can see the dimension 1 and dimension 2. Dimension of M1 and dimension of M2. And we can solve the problem by the Castelli equation and force analysis, and finally we get the equation of motion, and we can get the simulation figure. And this is my reference. Thank you.
So the question from the panel.
presentation. We thought it was really well made, and we have some brief questions for you. First of all, did you take the mass of the rope into consideration, or did you assume that it was negligible?
Can you repeat again?
Did you take the mass of the rope into consideration for this phenomenon?
You mean the
Whether the string had any mass?
I just ignore that, but I think it's an important point in this problem. But that's the reason why my situation can be a small error in my simulation. So I think I can improve it next time. It's a good point.
Thank you. Also, do you have, can you go back to some of the previous ones? Do you have error bars for all of those?
Because the sum error bar is too small to see. So
Okay.
okay.
And what were some of the factors that you controlled in your experiments?
Factor.
Yeah. Did you have any control factors that you held constant?
I control the coefficient of friction and the radius of the rod in the constant.
Oh, and can you go back to your simulation? Does that account for the multiple drops that you see in some of the special cases? You had this video of your simulation, but
Video solution. Release.
yeah. How does that account for the different drops that you see in some of the special cases?
The one will see like will go like this and it will go upper. It's just not like a spiral, like a perfect circle. It will it will go upper and go down.
But you got this from your system of equations, right? From a differential
Okay,
equation.
thank you for the question. So, 3 minutes for the preparation.
Thank you.
opponent have the floor, please.
I'm Ethan, and I'll be opposing the looping function problem, and I'm from the team all night. So the problem statement says, connect two loads, one heavy and one light, with a string over a horizontal rod, and lift up the heavy load by pulling down on the light load. Release the light load and sweep around the yard, keeping the heavy load from falling to the ground. Investigate this phenomenon. So we found that we believe that the key part of this problem is in the sweeping around part and the keeping the heavy load from falling to the ground. And we would first like to applaud the reporter for doing a great job in modeling both of these aspects. So this is the way that we think this problem should be approached. First, start with a qualitative explanation of why this phenomenon occurs. Then go into the forces such as by looking at a free body diagram and looking at how different forces interact in the system, how there's different forces on the light load and heavy load and on the rope, and finally investigating the effect of the relevant parameters. And these are the reported strong points that we feel that they did really well throughout this presentation. So first, they had a very clear video and track analysis that demonstrated how the phenomenon worked with a clear spiral. And when they matched this with their simulation, at first it seemed that it had a very clear match, and it showed how their theory contributed to their, aligned with their experimental observations. They also provided very clear background on the topic by introducing the Kaplan equation and the Atwell machine that helped build an intuitive understanding of the problem. And they also had a very clear free body diagram analysis showing the forces involved in this phenomenon. And finally, they tested a variety of parameters such as the length, the masses, all of these parameters that could have an impact on the system. They tested and had conclusive evidence of them. However, we have some suggestions that could make this report even better. The first is that the Kaplan equation can be more carefully applied. What do I mean by this? The Kaplan equation actually isn't applicable in all cases. And this is because the Kaplan equation is actually representing the boundary case where actually there's no movement. If you look at the derivation of the Kaplan equation, you'll notice here that the net forces are set to 0, and this is how you get the Kaplan equation. However, in the looping pendulum situation, this is clearly not the case, because especially at the start of this phenomenon, there's sliding, there's acceleration by the heavy load's weight, and therefore this is not 0. So we argue that the Kaplan equation cannot be directly applied to this phenomenon without further modification. Our second point is that this is a minor point. The reporters used the Euler's method for numerical analysis. We feel that using alternative methods like the Runge-Kutta or Livermore methods for solving ODEs can produce a result that has less error over longer periods of time. Another suggestion for the reporters, as we brought up earlier during the questions, is that they had some assumptions that were a bit overly idealistic. For example, they didn't consider the mass of the rope, which could have an effect in the acceleration of the system, as well as other effects like drag force, or the elasticity of the rope, or vibrations the system undergoes due to the contact between the rope and the crossbar. And finally, there were some small details where the simulation didn't fit the reality that we saw in the videos they played. For example, in the videos, we clearly saw that in some special cases, the heavy load stopped multiple times, then dropped again. But in the simulation, we didn't see that. And also, in the videos, we saw sometimes when the light load was spiraling around, there were different speeds for which it spiraled. It wasn't spiraling at a uniform speed, but we didn't see that in the simulation as well.
So we should move into the discussion. Okay.
Can you go to the slide where you apply the Kaplan equation? You keep going to where you added it into your differential. Yeah, here. Here, did you consider how the Kaplan equation is only meant to model the maximum boundary case?
Can you explain why it's a boundary?
Because if we have a capstan here, and we have a tension pulling on this side of the capstan, what the Kaplan equation tells us is the maximum force that can be sustained on the other side. The maximum force on the other side that I can hold with this force. But in the moving pendulum system, first of all, it's not the maximum because it's moving, so this side is actually more than what you have here. So why have you applied it directly? Because
because I assume that because I have two situations, but one is the velocity of the heavier load is bigger than mu, and I can know that the T1 is bigger because the friction force depends on the way I go. So if the velocity is bigger than 0, I can know the T1 is bigger than T2. So I can know that T1 is equal to T2 and mu.
I'm sorry, I didn't make my point very clear. What I was referring to was the fact that the Kaplan equation doesn't describe a case where it's moving. It only describes a case where it's static and it's at the maximum threshold. So why did you, because to apply to this case, you need some generalizations, and why do you think these are in order?
So you can see the derivation, and we just use the static coefficient of friction. So in my own derivation, I just change the static to the kinetic. So I change the static coefficient to the kinetic coefficient. So I think it didn't change any derivation of any problem will form in the derivation. So I just change it to the kinetic.
Okay, thank you for your answer. Can you go to the slide where you analyze the initial the effective length? Yeah. Can you quantitatively explain why increasing the length of the rope would result in a larger displacement?
It's simply because and when we decrease the length of rope, all the scooping handle scale will be bigger. So when we decrease the length, so the displacement of the heavier load will become bigger. Actually, I can really display this answer to you because the loop handler is dependent on many parameters. So we need another parameters to depend this phenomenon. So we can. So I just said in these cases because I didn't know the really all answer of this problem.
I see your point. So are you saying that this isn't a completely universal conclusion, but this is just what you saw when you observed?
Yes, this is
can I ask you about the assumptions that you made, that there's no drag force, that there's no...
actually, I have seen this problem before, and I put it in the back of my... And the drag force is every system. And,
yeah.
And when we think of this problem, we can find some... this problem will go more complex. And the drag force is equal to 0.1 times constant and times the density of air and this times the area and the velocity squared. But in my experiment, my area is not constant because when we doing a loop pendulum, the area will change. So if I consider the area center in my problem, the problem will be more complicated. So as I have a solution to this problem. Just change the load into a ball, and in any cases the area will be a constant. But this more hard part is if I change this to ball, how can I change the mass of the ball? So this is my opinions. So it's that.
So do you have any experimental data or any reason for why this would be negligible? Because after all, especially the light load is traveling at such a high speed. So in that equation there, because speed is a factor in this air resistance, because of this high speed, there should be a large drag force involved. So why do you think this is negligible over in the end?
I don't think it's it can be ignored, but in my discipline, I just need to ignore it because if I put I consider that area is a constant. It's not true true simulation. So I just ignore the every system and just say I'm just doing I just ignore it. So yes.
Thank you. So what do you think is the main force that's stopping the heavy load from falling? Is it the friction or is it the centripetal force pulling from the side of the light load?
That's the tension force. Because the force effect on the heavy load just gravity force and tension force. So the force keeping is from falling just the tension force.
So do you not think that friction between the rope and the capstan plays any role?
Because the friction is effect on the rock. So the rock tension depends on the friction. So to heavier load, the forces effect on him is just gravity force and tension force. The friction force is effect on the rock, and the rock affect the heavier load.
I agree with what you're saying. So there's two parts of this tension. There's a tension that comes from the friction, right? And there's the tension that comes from the light load circling around and the centripetal force from that.
Yes.
Which one do you think is more important?
I think it's because I have changed my coefficient of friction in my simulation. But I see if I in this page, if I turn the coefficient into the in my experiment is 0.1, and if I change the coefficient into 0.3, the displacement will go down, go up a little, just maybe 3 to 5 cm. So I think the physics of the lighter load will be more important.
Going back to your videos, you had videos showing the multiple drops of the heavy load. How does your theory, how does your the system of differential equation, how does that cover that special case?
The simulation can include this situation, but if we just imagine in our mind, we can solve this problem. But I just see it's in my observation. So, but my simulation can include this situation, and I can do a simulation line in it.
How do you get that? You do that by adjusting certain parameters, or?
No, just the program can solve this problem. I just put the equation and do a numerical solution. It will present this project.
Okay. Awesome. Going back to the capstan equation. When T2 is less than T1 times e to the mu theta, yeah. When the load side is less than the T1 times e to the mu theta, what do you think happens?
If the you can see I put the 2 sign here because the tension force, the capstan equation is dependent on the velocity. So
wait, can you explain that again? Why is the capstan different?
Because the friction force depends on the way it goes. Just move of 2 surfaces.
Wait, but don't we know from Amapon's second law of dry friction that friction isn't dependent on the velocity at which it moves?
No, it's the direction.
Direction. Okay. Yeah.
Okay, so when we have a direction, I can know the tension force of 2. So and when the tension 2 is bigger than tension 1, the heavy load will stop and the lighter load will speed.
Thank you.
Okay, thank you for the discussion. The opponent will summarize the discussion.
Oh, we had a very fruitful discussion with the reporter, and we had many points of agreement in agreeing that about some of the conclusions of the experimental data. However, we found that there are some main shortcomings in what the reporter presented. And one of these was in the universality of the conclusions that he arrived at. He mentioned that the conclusion is that eval only work for certain parameters and not all, and therefore the application of this to a larger scope is dubious in this case. Also, our largest point of contention is in the application of the capstan equation. As I mentioned before, the capstan equation only describes the maximum boundary where the system is held statically. However, because in this case, the system is constantly accelerating, and furthermore, when one side becomes less than the other, that's not the maximum boundary case anymore.
Okay, thank you for the summary. So questions to the opponent and reporter from reviewer.
I would like to ask the opponent that, so I can still understand for the interesting motion. Yes, can you explain again if your theory can represent the interesting motion? Can it?
Yes, it can. It can. The simulation can include this situation.
In some special conditions.
Yes.
But you don't know why.
I know why. I can explain it again. But I can explain it contextually. Because in this special situation, sometimes the tension for one was smaller than tension to one. Tension to one was smaller than tension to one. It would stop.
But you don't know why it happens, right? You don't know why it happens.
Because it depends on a lot of parameters. So you can give me a lot of parameters and I change to one. So
you know how to make these special conditions.
Yes.
You know how.
Yes.
And I would like to ask the opponent, while you previously mentioned that there are simulations about like neural methods or livermore methods. Do you think that really occurs? That really affects their experiment results?
Thank you for your question. We don't feel that it impacts it in a major way, but one of the key benefits of other methods like Roche Kudo or livermore is that if you extend the time period, the error doesn't, the solution you get doesn't diverge from reality as much. So especially if you're looking at looping pendulums on a larger scale or over longer periods of time, those solutions might provide more accurate answers. But again, this is a small point, and we acknowledge that the Euler method also works for this case.
So you would suggest that the reporter using other kinds of simulation skills instead of his now skills, right?
Yeah, it will be a small improvement, but not one that is absolutely crucial.
Important?
It will be a small improvement, but not one that is super crucial.
So it's optional.
It'll make it better, but it's not critical to this working.
And I would like to ask both of you that for the mass ratio problem, that do you think that the mass ratio is important or the mass itself is important?
Okay, I can answer the question. You can see this equation and you can see this any
mass inside.
It's just the mass ratio. But if we add the resistance in this, the mass will affect this.
So if you change, not changing the mass ratio, you change the mass itself, will it affect the result?
No. In theory.
In theory, you didn't experiment. How about you?
I did this.
I agree with him. The math says.
You agree?
Yeah.
Thank you.
Thank you. So 2 minutes preparation time for the reviewer.
Honorable judges, ladies and gentlemen, good evening. I'm the reviewer of Team Miracle, and today we would like to review problem number 14, looping pendulum. And the problem statement is that when there's a rod and you connect a light load and a heavy load over a rod, the light load will orbit the rod and keep the heavy load from falling down. And actually, that as the about reporters outlined, I discovered that their theory has very nice differential equations and simulations. But their experience is not bad, but I don't think it is enough while they did less experiments on mass and mass ratio. And for a conclusion, they are completed. But for reporters' pros and cons, first of all, they have nice experiments, videos, presentations, and serial analysis, and they have great observations that they discover some special motion. But I still don't think they have enough experiments. And for opponents, they notice very small factors and very strict. That I think it's a pros, but their cons is that I think it's too strict while they're digging on very small points that doesn't affect very a lot. And the discussion about the captain theory that the opponent doesn't say that the captain theory is always suitable. They need boundary conditions, but the reporter just didn't consider. So I would suggest that the theory is not strict enough, you need more work, but you can try to explain that why it fits if the factor that the opponent said is not big enough to affect. And they have interesting motions that a reporter simulated it, but can't explain it physically. And I think they need more work on experiments so we can detect the forces. And I asked about the simulation method, about the opponent, but he said that it's not that important, and I agree with him. I think that it's not necessary. And I asked about the mass ratio, but actually both sides agree with the reporter that in their theory, only theory, the mass ratio affects these parameters that you want to measure. But this is only on theory, and I think the reverse point is, if they consider air drag, what they didn't do, well, it still remains the same, and so they didn't do any experiments that prove the mass ratio is more crucial than the mass itself. And this is a missing point. I would like to suggest these experiments can be done so the question would be more complete. And they also discussed about the mass of rope and air drag, which air drag I mentioned before. If this is discussed, then well, mass ratio changes. Mass of rope, I also think that it doesn't really affect a lot. And here's my review. Thank you for listening.
Thank you. The reporter present your concluding review.
Okay, it's my conclusion remark. And I think the opponent gave me a good suggestion that we should consider the weight of the rope. And I think the opponent said I should consider the air resistance, but in my simulation I do the factor of the air resistance, but it seems not very important, but a little less 0.5 or 6 centimeters. And I did the experiment of the mass ratio and mass, and yes, the mass ratio just it affect the result of the problem in theoretical, but in reality the mass will affect the result because of the air resistance. So air resistance should be considered, but in my problem, in my experiment, I just ignore it. Okay, and the problem of the captain equation, I have an explanation. Because in the beginning, the loop pendulum just spin around. So the captain equation should be the maximum boundary. But when the heavier load stop, the captain equation is not suitable for you. So when the heavier load will stop, my program just don't use the capital equation, just use the simply for the analysis to the simulation. And I think it's my concluding remark except for the components and review. I think.
So it's time for the question.
Is that okay then? Can you explain this spatial motion right now?
I think in this special situation, because in this situation, because in I said it's a simple in a simple case, the tension force when heat is standing, the tension force once should be bigger than the tension force because the heavier load just keep falling. But when the heavier load was stopped, it's not suitable for use of capital equation. So in this special situation is that when the tension force 2 is bigger than the tension force 1. In this situation might be the length of rope was bigger, like 17 cm, or the mesh ratio was smaller, like 1:4 or 1:3. What happened in this situation?
Do both of you agree with me? Do both of you agree with this?
One explanation, I think is true. Over there, the switch from T1 greater than T2 to T1 less than T2, I don't believe that necessarily means that the system stops. And that's because if these two forces are equal, that only means that there's no net acceleration. But there still could be velocity. So I don't believe this is the exact point where the special motion occurs. And that this isn't a very good explanation.
How about your opinion?
I agree with the opponent.
Okay, so they think even these two tangents equal each other, but they still might have a velocity going on.
Yes,
Right?
it must have a velocity going on, but no. In the second S equal, there was no acceleration, but they still have the velocity, so the sloping pendulum will keep going on.
If you look at your data, I remember there's a figure. Why the arrow is so large when the release angle is different? If you go back to your, yeah.
Okay. Because when we put when we release the lighter load, sometimes the initial places is not quite different in reality, just because in the simulation the heavier load can be placed at a fixed point, but in reality I just control with my hand. I can just two accurates.
No, I still don't see a difference. I mean, you are saying that, for example, 30 degree or 60 degree, you will have a external force. You put an external force on it.
Just the heavier load is put on the below the rod, right? Just the heavier load place is below the rod. Yes. So when I put it might in different initial.
But did you see this in your simulation?
Because in simulation I can control its constant. So this problem just appear in the reality.
So another question. If the mass of rope is is very important, how come you have, for some cases, your simulation fit very well with your experimental data? you always have problem of the mass of rho, right? Because you don't consider this case in your simulation, right? But in some cases you fit very well.
So maybe in true situation, maybe this is right and this is wrong. Maybe in true solution of the problem.
So that's why I'm asking, do you think this is really important?
Yes. Because the washer, the small washer I use just maybe 6 grams. So the level rope is have a very big mass in this experiment.
Any further question from the chair? Okay, then we have a short question. If you think the capstone equation is not a good model for this one, what do you think about their good fit between their simulation and experimental data?
He mentioned earlier that when he was doing the simulation, he could fit a lot of constants to adjust the simulation so that it fit the data better. Was that clear? Like, because lots of the constants, I don't think was measured very exactly, so those could be adjusted in the simulation to fit the data.
Thank you. Okay, so it's time for the juries to figure out the score. Okay, so let's show first the score for the reporter. Seven. Okay, so now let's show the score for the opponents. 88978. So let's need to show the score for the reviewer. $88776. Okay, thank you, and thanks for the attending to the